Okay. Okay, welcome everyone. Sorry we got started a couple of minutes late here. This is the Databases on Wrangler training. My name is Chris Jordan. I lead the Data Management and Collections group here at TACC, and I'm one of the co-PIs for the Wrangler project. I'll be giving most of the presentations today, along with my colleagues Niall Gaffney, who leads the Data Intensive Computing Division here at TACC, and David Walling, who's a member of the Data Management and Collections group. Let's see if the slide's advancing here. Yeah, that's what I'm doing. Oh, there we go. All right. Slides are lagging a bit there. Okay, so just quickly, what we're going to do today, I'm going to give a real quick introduction to Wrangler, just in case anybody is not familiar with it. Just give you a sense of what the hardware is and what the system is designed to do. Talk for a little while about what database technologies are available, kind of in general, and how you interact with them. Essentially, to try and provide background for the next section, which is what options are specifically available on Wrangler and how do you access them. That will be the majority of the overall presentation. In the middle there, I'll try and stop for about a 5 to 10 minute break, just because this is going to be about 2 hours probably in all. So you may want to break in the middle there. We'll also have an opportunity to take questions at the end of that first presentation, and again at the end of each of the individual presentations. The last two presentations will be David Walling talking about what it takes to kind of populate and maintain data in your database. So a broad range of activities that we collectively refer to as ETL, extraction, transformation, and loading. And then finally, Niall will talk for a few minutes about getting an allocation on Wrangler for databases, just so that once you're finished with the training today and excited about using Wrangler, you can immediately go and request an allocation and get started. So like I said, we'll try and move quickly through the presentations themselves without pausing for questions, but there will be an opportunity for QA at the end of each of the presentations. There's also an online chat available, and we should have a couple of folks in that chat room, and they may be able to answer questions if you have them during the presentation, or they can hold them for the presenter at the end. Okay, so quickly, Wrangler in 10 minutes or less. Wrangler is a system that's funded, supported by the National Science Foundation, the Advanced Cyber Infrastructure Group, and we acknowledge their support gratefully. We have a couple of partners on the project. Besides ourselves, Indiana University has another component of the overall Wrangler hardware. I'll talk in more detail about what specific pieces those are. They're also contributing in terms of end-to-end network tuning activities and helping us administer some of the replication systems to preserve data across multiple sites. And the University of Chicago is providing support for the Globus Online data transfer mechanisms and some additional mechanisms associated with Globus Online for things like data sharing between us and other XSEDE sites. And the machine itself consists of Dell servers and DSSD, which is now owned by EMC, high-performance flash storage. So the idea with Wrangler was essentially to deal with problems that are really oriented around data and to do so in multiple dimensions. There are data-intensive issues at the small scale, and there are data-intensive issues at the large scale. It's data-intensive does not just mean you have a lot of data. It means your problem is centered around data, and there's lots of ways in which data can be kind of the driving factor for your problem or the limiting factor for your problem. So there's a wide range of applications and interfaces. Hadoop is one that comes up a lot, but it's by no means the only big application in this space. There's lots of kind of more traditional statistical analysis and mathematics packages, things like R. There's geographical data, which I'll talk about to some extent today in combination with the database stuff. The database stuff is obviously the most relevant here. Fairly obviously, database workflows are organized around data. And to support the full data lifecycle. So we have some unique aspects of the way that Wrangler is allocated and used in policy terms as well. You know, we have metadata and collection management support. We support storing data for the lifetime of a project rather than just over shorter one-year terms. And we support data collections as a valid allocation within the XSEDE context, whereas the most resources really are focused around computation and what new research you are doing rather than what research you might be enabling through data and data sharing mechanisms and platforms that are built on top of data. And I'll talk more about what those platforms might be later on. So the specific hardware that constitutes Wrangler, so there's a 10 petabyte replicated disk-based storage system. So what that means is it's actually 20 petabytes of storage, 10 of which is here and 10 of which is in Indiana, and data is replicated between them. We have an analytics capability that consists of 96 compute nodes with several thousand cores in all. Each of them has 24 cores. 128 gigs of memory on each of those, and those are the newer Haswell CPUs, so they have particularly good memory bandwidth. They're particularly good at moving data through the system. And we have the high performance flash storage subsystem, and we've got some numbers here about the kind of collective performance you would expect to get out of the overall flash system. On individual nodes within the cluster, you won't get these kinds of headline numbers as with any cluster, but the flash subsystem is very, very fast. And I'll talk a little bit about what effect that might have in a database context as well later on. All of these are interconnected with an InfiniBand network, and there's a PCI-based interconnect to the flash system, which is basically the lowest latency, highest performance connection you can get. So as you can see, and I already mentioned, there is an Indiana component to it. That's the other 10 petabytes of disk storage that's replicated. There's also 24 nodes up there that can support databases, just like we support them here, as well as some analysis and other capabilities. Basically anything you could do with the systems down here, you can do with the systems in Indiana, except that they don't have the flash subsystem there. So I think I already talked about this. I won't go into much more detail on the nodes themselves. They're certainly more than sufficient for most database-related needs. The DSSD storage subsystem, this is the innovative capability in Wrangler. This is the thing that really makes it different kind of qualitatively from other systems that are out there. So this is not SSD, it's not drives, it's PCI connected flash. So you have the full performance of the PCI bus, you have the lower latency of the PCI bus, but you also have kind of a collective connection capability. So the limits are not Ethernet or InfiniBand, it's the PCI bus performance. And it's connected to all of the nodes. This is really important. This isn't like a normal flash drive that you would put into a node. It's a global pool of flash-based storage that's available to all of the nodes. And this will be particularly important in the context of something like the transient databases I'll talk about later on, where your database could end up moving around between nodes. That doesn't matter from the standpoint of accessing your data and accessing your data at high performance. Yeah, so something that's important to understand when talking about Wrangler, because we are trying to support data intensive computations on the flash, because we're talking about dealing with bodies of data that are essential to your work. We try and model research or computations in the context of campaigns and allow you to have long running reservations on the machine to support those campaigns. So when you get a certain number of jobs, you have a certain amount of flash that's associated with that you're able to stage data into the flash, and you're able to compute continuously on that data for the length of your reservation, rather than having to submit individual 24 or 48 hour jobs, which are kind of the typical limit on a system like Stampede. You will still use jobs most of the time within the context of a reservation, just as a way to initiate your computation. But the idea is that you essentially claim a part of the machine and you hold it for a certain period of time while you get your work done, so that you're not constantly dealing with data staging kinds of issues. We do have a couple of long-term file systems in addition to the flash associated with Wrangler that's kind of important to know about, besides the kind of standard home directory that you would always expect to be there, and which you, in the context of Wrangler and kind of TACC at large, you shouldn't usually think of home as a place to store much data. It's where your config files go, where you might, if you need to edit temp files, you might do that there. But all of your data really should be stored on someplace like work, which in this case is global. So it's the same work file system between Wrangler and Stampede. So if you have data on Stampede that you want to process on Wrangler, turns out it's pretty much already there. And that's kind of where most large data should go, unless it's specific to Wrangler. We also have a /data file system. This is the 10 petabyte disk-based storage that I was talking about earlier. And obviously there's a lot of capacity here. So, you know, this is where your big files associated with Wrangler should go, unless you need them on the flash for active computations. This is also where a lot of the disk-based database storage is going to be on the /data file system. So that's the quick overview of what Wrangler is, and there was a more detailed discussion of Wrangler in a training just a couple of weeks ago, and that should be available to you online if you want to kind of get more of the details of Wrangler as a system. You can go and watch that. So I'm going to go directly into the overview of database technologies now, and essentially the kind of issue here is that there's a huge number of options really available now, and I think particularly now because of the flourishing of the open source world and the startup internet world, there are a lot of folks out there doing technology development, and a lot of it is focused around data and organizing and using data as quickly as possible and as effectively as possible. So there really is an enormous amount of innovation in this area right now, and that may be, you know, more than anything else, the kind of big story in terms of what people talk about as big data. It's as much the amount of innovation that there is and interesting development going on around different ways of managing and dealing with data, as much so as the availability of lots and lots of data and different ways that people are using it. So I'm not going to try and cover the entire terrain by any means. We don't have time for that. I'll try and focus on some of the most robust, some of the most widely used options, certainly some of the more established options, and also to a certain extent some of the places where the unique capabilities of Wrangler may actually make the biggest difference. But there are certainly an enormous number of resources available on the internet if you're interested in other things or things that we don't talk about in much detail in today's session. So I want to talk a little bit about data models. When you're thinking about using a database, when you're trying to select a database, one of the kind of most fundamental options you're going to have to deal with is, what data model am I wanting to deal with? What's the model that best fits my data? So the relational data model is kind of certainly the most established, the most widely used. It's an extremely flexible model. I'll talk a lot more in detail about what the relational data model is later on. But there are other models for how your data is constituted and structured. Object orientation is one that you may be familiar with if you're familiar with programming at all. And the idea is that the actions are kind of bundled together with the data. Functionality and data are attached to each other, even in the context of a database. And that's kind of an interesting way to think about databases. There's also graph and network databases where what you're modeling is a collection of interlinked items, and you want to do graph and network kinds of analysis and computation on them, that may be an appropriate kind of option for you. But we'll mostly talk about relational data here. Primarily that's because this is, you know, by far the kind of most dominant model in the computer science world. The most established options use a relational data model, and it's been around for a long time, and it's been tested pretty well. And in a lot of cases, other models can be encapsulated within a relational data model. So you can do network or graph data within a relational database without too much trouble, and sometimes they're directly supported. So it's kind of the best way to cover the widest range of use cases. So a few kind of simple concepts that we'll be talking about a lot here. So we're talking about structured data here. A record is a single instance of data structure. So structured data is essentially a whole bunch of records that have the same structure. So an address book, a CD catalog, those kinds of things, transactions that a bank is storing. Those are all the kinds of things where you have the same set of data time after time after time, and it's the relationships between that structured data or the cumulative impact of all of them that's important. So a record is a single row in a relational database context. A column is essentially all of the rows of a single data element. So in an address book, it's all the last names would be represented as a column. A table or a relation is just a collection of these things. So again, all of the addresses in the address book. A key is an element that occurs in multiple tables and is used to link them. I'll show you an example of this, but a simple example of this is, you know, any kind of user ID, right? If you have a user ID in the context of TACC, that user ID might be associated with lots of different information about you. It may be associated with that information in different tables, and it's essentially used to link you across all of those tables. It's used to say, you know, this is this person, rather than saying, oh, well, this name is the same between these two records. I think it's probably the same person. It's a way to deterministically say, no, this is the same person because I'm using the key to link them. An index is often associated with a key because in many cases when you're working in a database and you create a key, you're also creating an index or vice versa. But basically it's a kind of secondary data structure that's used for accelerating access to records. So this is a really important concept in relational databases. If you have something that you know you're always going to be searching for, you know, like a user ID, you can create an index on it, and essentially it tells the database, create another data structure that makes it easier for me to find these really quickly. A query is just a command issued to the database, and I just wanted to say that because a lot of times when you're talking about databases, you'll talk about queries. A query in this context does not always mean a question. It means something that you're telling the database. You can execute a query that's actually adding data to the database. So I just wanted to point that out. And a constraint is just a limitation on a specific data element, usually a column. And it's, you know, going to be something like, well, this value has to be an integer less than 1,000, or it has to be a positive integer, or it just has to not be null. That's when you see really, really frequently when you want to ensure that a particular column is always populated, you can put a constraint on it that says not null, and you can't put data in the database if it doesn't satisfy that constraint. So you can kind of see already some of the kind of key characteristics of databases and structured data. They're enforcing the consistency of your data, or they can enforce the consistency of your data if that's something that's important to you. So SQL is kind of the most common way of interacting with relational databases. It is a standard language for defining and querying structured data. It has a data definition language and a data query language. I'll give you some examples of it in just a minute. And it is really appropriate in any case when you've got, you know, real consistent structured data. systems that interpret SQL are typically called Relational Database Management Systems, or RDBMS, which is an easy acronym to say. And I've given a couple examples here of what we support that are RDBMSs. MonadDB is kind of an interesting borderline case. We won't talk about that too much today, but that's another kind of pointer for those that want more information. So what does SQL look like? I just wanted to show you this in case you're not familiar with it. It may not necessarily sound very user-friendly, but actually it's not very difficult at all. So here's some simple examples. Creating a table, you have a table name, you have a structure here. It's saying I have an identifier, that's an integer value. That you might also say that's a key, and you can say that in the table definition if you want to. You have a name, and that's just a bunch of characters, and you have an address, and that's a bunch of text. All right, and so what you're saying is I'm going to create a table, I'm going to put a bunch of rows in the table. The rows will always conform to this specification. And you can also put constraints in here like I was talking about. So you can say, I have to always have a name and an address in my records when I put data in, so that you don't get bad data in there, and which can then cause problems later on when you're doing your analysis. Insert into table name, that's an example of populating the table. So what would go in there where I've got data, that's going to be a row. So it's just going to be a bunch of values that conform to the specification of the table. And you don't have to say, if your data conforms to the whole table spec, you don't have to say, oh, this is the ID, this is the name, this is the address. It can tell by the context, this is the table you're putting it into. First field is an ID, the second is a name, the last one is an address. So it can make it fairly easy to format data for adding it into a table if you want. And then if you want to query it back out, there's a select operation. You're saying select all of the names from the table name where the ID equals 6. And basically if ID is a key, you're going to get one result because it has to be unique. And yeah, so all of these operations are performed on one or more rows, and that's kind of the metaphor that a relational database uses. So if you're thinking about select name from table name, you're basically saying which fields from the rows do I want to show if it satisfies this constraint, and it's thinking of everything in terms of rows. So there's this thing called ACID that kind of is a useful acronym that summarizes some of the things that are considered to be really important in the database world, particularly in the SQL world. And you'll often hear about databases in terms of their ability to conform to or implement these ACID properties. They are atomicity, which means each thing that you do is done in isolation. It only really affects itself. Consistency, you have a consistent state before and after an operation is performed. And so that's, getting back to that, the notion of half-filled data or broken data. The system is meant to ensure that once you've defined what the rules of consistency are for your data, and it will maintain that consistency, and it won't let you do things that will break that consistency. Isolation. So basically, this is just about whether you perform operations serially or concurrently. So you can think about this again in terms of bank transactions. If you're moving data from one account to another, you're decrementing one field and you're incrementing another field. That is two different operations if they're two different accounts. And what this is saying is it doesn't matter whether or not you do those one after another or at the same time. And so that can be very important. Again, this is all about maintaining the consistency of your data over time in situations where you may have lots of different things happening at the same time, or you may be performing complex transformations on the data. It's a database that implements these kinds of ACID properties is going to always maintain the consistency of your data despite different things that it might do under the covers to reorder operations, despite things that you might do to change the order of operations, all of those things. And durability, obviously. If you change something, it stays changed. And this notion of a transaction is very important relative to the ACID properties, because you can define what constitutes a transaction. All of these things are defined in terms of a transaction, but a transaction could actually be a whole bunch of things. And what that means is, again, in the bank example, if you want to do those two operations to the accounts, you can bundle them together and say, this is one transaction, and it will treat that as an atomic transaction, which means either the whole thing is done or none of it is done. You can't get halfway there and have something break and it leaves you in that half completed state, right? And so that's why the notion of transactions is important, and that's why it's important that you have the capability of grouping things together into a single transaction, so you can't essentially break your data. Another couple of things that are important, stored procedures and triggers. Essentially, these are ways of telling the database that you have complex kinds of sets of operations or complex queries that you want to be able to do again and again, and that in some cases changing one piece of data may change another piece of data. So a stored procedure, one way to think of it is like a function in a programming language. It's a way of grouping a bunch of things together and saying, well, this is a procedure, I want to give it this name, and I want to be able to invoke all of this using a fairly simple call, just like a function. And a trigger is a good way to think about it is like a policy or a rule. It's like saying, when this thing happens or this thing changes, you also have to change this other thing. So you can essentially define complex groups of tables that have relations to each other, and you can use something like triggers to ensure that simple changes you make to one table then actually propagate out to other tables, or if they have consequences, those consequences are recorded. Or one really kind of broad example would be, you could create an audit. You could say trigger on any kind of insert operation, and the trigger is going to launch a procedure that basically adds a new row somewhere saying who made this change, right? So you can create an audit table very easily saying, when somebody changes something, record who changed it, what they changed, and when it was changed. And then you've got an audit. So these are very powerful concepts, and they allow you to define important aspects of your data, not just kind of at rest, but as it changes dynamically over time. So here's just a graphical example of kind of what a relational data model looks like. So you've got 3 tables here. So you can see pretty obviously why you talk about columns and rows. This could be something in a spreadsheet, and you would call them the same things. The important thing to notice here is the lines that are drawn between different columns in the graph are representing keys that are shared across tables. So you can see you've got 2 fields in 2 different tables named author ID. And those values are used to link the authors across, not the name of the author, the ID. And that's a separate thing. So you can have multiple authors with the same name, they'll have different IDs, and you'll be able to uniquely distinguish them and maintain links to them across tables. And the same kind of thing with a publisher ID. And this is kind of the relational aspect of the relational data model. So how do you interact with databases? In almost all cases, it's a client-server kind of system. SQLite, and there's another couple we might talk about briefly that are essentially libraries that you could think of as an exception, but really almost all of these are client-server systems, and the interaction model is always going to be a kind of client-server thing where you've got one or in some cases several server processes living somewhere on a network. Sometimes if it's a more cluster-oriented kind of database system, you might have a head node, although it's typical to make those more kind of uniform. And you can run a client really anywhere on the network, and you can communicate with the server via network protocols that are usually standard, certainly in the case of SQL and RDBMS. They're generally standard protocols and SQL, or in some cases a database-specific language. And a lot of these databases have their own database-specific extensions to SQL that will look like SQL, but might give you one or more features that aren't in the SQL standard. And I think if any of you have worked with computers much, you'll be familiar with that phenomenon. So different ways that you can access these database servers. There's direct clients. I'll give you an example of those later on, basically a command line or a graphical shell. There are graphical shells, but typically it is a graphical shell. So it's going to give you a window in a desktop, and it might give you some graphical tools for manipulating the text. But the fundamental interaction model is just like a command line, a shell kind of interface. There's various APIs. Similarly, a lot of the APIs are just going to be ways to issue SQL commands to the database and then store the results as a string or something like that. And then finally, ODBC and JDBC. These are just the standards used for connecting and interacting with these databases remotely. So you can have a single ODBC implementation that could work with MySQL or Postgres or Oracle or any of those, or all of those. And these are particularly useful in the context of applications. If you have an application like SAS, you don't want to have to write a module for it to work with Postgres and one for it to work with MySQL and one for it to work with Oracle. You write it to work with ODBC, and then the operating system and the ODBC drivers handle all of that translation into and out of the standard. So some examples of where this stuff is used. Web backend is by far, numerically, that's going to be by far the most common example. Mostly that's going to be MySQL. You may have heard of LAMP as kind of a standard web stack. M is MySQL in the LAMP stack. And so it's basically used as a place to store web application data like usernames and passwords. And a lot of the most common and biggest hacks that you will hear about where people steal usernames and passwords are people breaking into a MySQL database and getting all of the contents of the web application database. But you can also store domain data in the database, even if it's backending a web application. So wikis are a really common example of this, where you have the text of the wiki is basically stored as database rows. As well as the username, the password, all of that kind of profile information. Something we see a lot of in the database application realm is large tabular data sets. So there's a lot of folks out there that have tabular data sets. Typically, they start by putting them in an Excel or some other kind of spreadsheet. Eventually, that spreadsheet gets really, really big. A spreadsheet is a perfectly valid way of working with tabular data, except when your data has thousands or even millions of rows, it starts to get clumsy. So it's very easy to go from a kind of really big table in a spreadsheet into an SQL engine. You can go directly there, or you may want to decompose the data somewhat, split it out. If you've got a whole bunch of columns in your spreadsheet, you might want to break it up somehow and generate a table or a set of tables, more like what I showed you earlier. And then SQL turns out to be a really powerful language for selecting subsets of data, which is kind of what you could argue it's designed for. So you can connect to a database from a tool like R or SAS, and you can say, you can essentially do kind of the first step of your analysis. If you have survey data in a really big table, you can say, well, you give me all of the responses from men, or give me all of the responses from women over the age of 35. And then you can do more analysis on that subset of data, but you can select interesting subsets really easily and then work with those subsets in a more rich statistical analysis package. And then you can even do more complex kinds of applications in the database as well. There's some kind of bleeding between these. I know at least one example of a website where a lot of the kind of core functionality of the website itself is really in the database and in the way that the database has very complex rules and policies around the way that the data is structured, so that people who are relatively naive about things like data structure can work with data, can input new data, can verify data without necessarily having to be technically proficient in the data structure, but the database kind of enforces consistency and in some cases fills in things that they may not know. And of course, there's, SQL, something I'm not really showing a lot of, but SQL is in fact a very rich language that has functions of its own. It has a lot of mathematical operators. And of course, it's really good at things like comparisons and pattern matching and those kinds of things. So you can actually build some fairly complex applications in SQL itself if you want to, if you aren't a programmer or if you don't see the need to go beyond a database. I think you should always use the minimum number of tools that you need to get a job done. So one example is this OrthoMCL application. This does grouping of orthologous protein sequences. Basically, it's looking for protein sequences that are roughly similar to each other within certain kinds of bounds. You can take BLAST, which is a genome sequence recognition tool. You can basically use it to produce big lists of genes from a sequencer output, and you can take that and put it into MySQL, and basically you get a whole bunch of genes, which you then can use database operations to compare to other lists of genes, look for certain amounts of similarity, generate new tables based on those, do statistical analysis of those things, and then dump them back out into a format that you can graph and look at visually and hopefully derive something interesting. But the kind of important thing about this is, this is a full-blown kind of application. It works on gigabytes of data at a time. It can run for hours, but it is really almost entirely in the database where the application logic lives, where the execution happens. So this is an interesting case for us to run on a cluster because we'll have folks who want to come and run the application on the cluster. But it turns out where they run the application is really in the database, and that in the past has not been on the cluster. With Wrangler, we have the capability of putting it on the cluster, and that makes a really big difference. So I'll talk a little bit more about a couple of examples of SQL RDBMS engines here. Postgres, these are the ones that I'm going to focus on right now, are the ones that we support on Wrangler out of the box. Postgres has been around for almost a couple of decades now. It's very mature. It is focused on standards compliance, on these kinds of ACID properties increasingly, and on reliability. So they spend a lot of time in the Postgres development focusing on things like data consistency, the reliability of the process. The kind of downside of that for a long time was that things like multi-threading were not supported. Performance wasn't necessarily the best of the options that were out there. I think a lot of those things have improved in recent years as they've kind of gotten they've gotten most of the standard implemented, besides the things that are really, really hard, and they've focused more on things like multi-threading support and other features that are important to the database community. This does, I think, support, in the open source realm anyway, this supports by far the kind of widest array of the SQL standard operations. MySQL has improved a lot, I think, in the last decade, but Postgres is still, because it's focused on providing the best SQL standard support, still probably does. So if you want to do advanced things with SQL, Postgres is probably your best option. Unless you want a commercial solution like Oracle. MySQL, in contrast, at least initially, was a little more focused on being the easier one to use. That was kind of, I think that probably more than anything is why it became the M in the LAMP web stack, because it was quick and easy to deploy a MySQL database on a local host, connect it to your web application, and get up and running when compared with Postgres. It is an open source database. It was supported by Sun for a long time, then Sun got bought by Oracle. Once the Oracle purchase of Sun happened, there was a fork in the code base, and there's now at least two kind of large alternatives to MySQL that are based on the MySQL source, and to a certain extent still try and stay aligned with it, but are no longer part of the core MySQL distribution. That's important to us because Wrangler uses the MariaDB alternative to provide MySQL support. It is meant to be compatible in almost all ways. You can use a MySQL client with a MariaDB server. Those kinds of things are all supported. But these alternatives provide some features that have essentially become enterprise features in the Oracle MySQL distribution. So if you want to have certain features, you can either pay Oracle money or you can use an alternative to MySQL, and we've chosen to use an alternative to MySQL. The plugin architecture is now, I think, one of the more noteworthy aspects of MySQL. So there's plugins for the storage engine and for the authentication, and I think for other aspects as well. This is really important if you're interested in novel ways of manipulating data at the very low level. So the storage engine is essentially how data gets reorganized and written out to disk. And there are lots of different ways to do this. And this is a lot of what technically databases do, is kind of reorganize data and write it out and read it back in ways that are meant to optimize for certain applications. So in the MySQL world, you can write your own plugin that will do it how you want it to be done. Or there are different options that do it in different ways that are optimized for different kinds of workloads, essentially. So there is an archive plugin for MySQL that's really optimized for read operations, and it doesn't do writes really fast. But if you're running a data warehouse, then that might be the best kind of solution for you. So that's an important feature. And the plugin for authentication obviously is important because we live in a complicated world with lots of different ways to do passwords. And in our case, we want your TACC password to work to access your Maria or MySQL database. And this allows us to do that. But it is not as focused on things like ACID compliance and the SQL standard as Postgres is. So there are ways in which you can break the spec. It's probably not as important unless you're really focused on kind of a highly transactional database, something that's a big web application with lots of users. But if you are doing something like that, then it may be very important to you. So NoSQL, I just kind of wanted to mention, NoSQL is a term that's used very broadly for a whole range of databases that essentially, they may in fact actually support some of the SQL language itself, but I think kind of the way that I try and generally characterize them is that you're trading off one or more of the characteristics of a typical SQL RDBMS in order to get some kind of reliability gains or performance gains, usually by spreading operations out across multiple nodes. So that you can do more, so you can have more fault tolerance, or so you can apply multiple nodes worth of performance capability to a problem, or simplicity. If you have a very, very simple problem where your data has a very simple structure, then a NoSQL option may be much more efficient for you because you don't need all of the features that Postgres provides. You may just want a key value store, essentially a glorified big hash table, and there are NoSQL options out there that will do that and let you build really, 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 really big hash tables and access them really efficiently. And so that's probably the biggest reason that you would choose a NoSQL option, is because you have data that has a structure that really matches well with one of these NoSQL solutions. And there's a few examples here of the kinds of data structures that you see. Columnar data, essentially, this is data where the way that you want to manipulate it and work with it is really more focused on the columns as opposed to the rows. So if all of your operations are going to be on, all of the last names in the database, and that's really all you care about, rather than picking out a few last names, then the columnar store may be more efficient for you. I talked about key value pairs, and then there's a kind of wide range of things that are expressed as either JSON or XML data where it's structured but without a real hard schema. And there are tools that will allow you to work with that. Yeah, so I think I mostly covered this. If your data doesn't match the relational model, if it matches something else better, then this is why you would choose NoSQL. The other reason to do it would be if you need node parallelism. If you have a problem where just the scale of the data is such and the way that you want to access it is such that you need to look at all of the data to get an answer to your query, and your data is on the order of terabytes, then you might want to apply node parallelism so that you can have multiple nodes working on this problem at once rather than just waiting for one node to chew through all of the data. Or it may be too big for one node to hold in memory or something like that. A lot of the NoSQL options are focused on this kind of thing because a lot of these are coming out of that internet startup world. You know, if you're Google, the size of your data set is such that you cannot efficiently deal with it on one node. You can't really deal with it at all on one node, but you certainly can't do so efficiently. And so you have to have node parallelism. And you have to have systems that are robust and fault tolerant over wide area networks. And so there are lots of interesting things that you're going to do in a software package to support that are not necessarily consistent with a typical SQL relational database kind of model. So MongoDB is one example of a NoSQL database. It is in fact NoSQL. It has its own Mongo-specific query language. They might actually call it MQL or something like that, Mongo Query Language. It is document-centered. Basically, this means it's working on JSON documents rather than on rows of a database. And so it doesn't have any notion of a predefined schema that you must conform to. You can impose a schema in your application, but Mongo doesn't care. You can put data of completely different formats in a Mongo database, and it will not have any problem with that at all. So this can be interesting. This can be valuable in particular if you've got cases where most of your data is of the same schema, but then you have a few things that may slightly vary. So you might need a couple of extra fields in isolated cases, but you may not always know what those extra fields are going to be. So this might be a good option for something like that, where you mostly want data to be uniform, but you need the flexibility for it not to be uniform in cases where the actual data itself is not. And it does have node parallelism. Essentially, it shards databases. This basically means it breaks up the database and puts chunks of it on different nodes. And so you can operate in parallel on the same database using multiple nodes, but it's on different chunks of the same data. Yeah, so JSON, if you're not familiar with JSON, it is a lot like XML in terms of the structure. You just have a bunch of attribute value kinds of pairs. They can be nested. There isn't an inherent schema. I don't know if there's a JSON schema language as there is with XML. There is. But I guess the kind of important thing is here, you can have a schema, but it's going to be your application, your client operations that are going to define and enforce that. It's not necessarily going to be Mongo that's going to enforce that. So that's another kind of characteristic of the NoSQL options in general. They're not going to be nearly so featureful in terms of allowing you to define what constitutes consistency in your data and in enforcing it. They're a lot more willing to let you do whatever you want with the data. That may or may not be shooting yourself in the foot. It may be essential for what you want to do, but it's something to be aware of. So you can have a schema, but it's going to be something that's mainly maintained inside your application. You can get outside of it if you want to. Obviously, you still need to pay attention to data structure if your data is structured and if the structure is important to what you're trying to do. Okay, so I'm going to talk for a few minutes here about GIS in databases. So this is Geographic Information Systems, geospatial data. And basically, geographical data is, essentially it's going to be a collection of entities that represent points in space. And there are now standards, we'll talk about that in a minute here, that define how you are going to store those points in space in a way that's shareable across platforms. But kind of the key point is that this is a really classic example of structured data. You have stuff that you know is going to be consistent time after time after time. Being able to do different kinds of operations collectively, being aware of the structure is really important to effectively working with the data. So you have here some examples of the kinds of things you work with in a GIS context. You have points, lines, and polygons. And pretty much, anything that you see on Google Maps, anything like that, that's all using GIS. Mobile phones, probably 90% of what people do with mobile phones anymore includes GIS. Data, and in fact, you may or may not be aware of it, but a lot of the time when you're interacting with websites now on a mobile phone, the website will ask your phone, what are your GIS coordinates? And it may or may not do anything with that. But if you ever wondered why Google might come up in Japanese just because you happen to be in Japan, well, that's how they know. Like I said, storing spatial, it's just like any other data type in a database. You're going to have some kind of geometry that maybe a point, maybe a line, polygon, but it's going to have some kind of really complex and essentially meaningless internal representation that's shown here. There's a well-known text interpolation of that. But it's essentially kind of raw data that the database needs to do some additional processing on or transformation on for it to be meaningful to you or to an application. So this is kind of interesting. You need a spatial reference system. You can see in the bottom right-hand corner here, there's a few different examples of different projections of points around the Earth. So if you're getting these numerical coordinates that represent points on the Earth, you have to understand what's the reference system that these points exist in, and those can actually be global or local. It can be projected or non-projected. And this is I think typically this is all kind of handled by the GIS layers and by the GIS software. You don't necessarily need to manipulate this directly. You just need to know that it's there. It's a potential source of problems. So a quick tour of kind of what supports spatial data types. So you saw there is a really kind of specific format in which this data is expressed, and you don't necessarily have to have a database that supports these types, but you're going to have a much easier time of it if your database does have some awareness of that. The database will be able to do the kinds of operations that we've been talking about with an awareness of the spatial nature of the data that you're working on, as opposed to just working with points and then essentially making your application implement all of the logic. So, is this point within this polygon? You can write the logic to figure that out yourself, or you can use a spatial database and just have it do the work for you. And in terms of productivity, obviously, there's a big difference between those two things. So Postgres has these PostGIS extensions that are supported on Wrangler that can do this. MariaDB has native spatial data types. I don't know how robust the overall framework is in terms of working with the spatial data, but it does have awareness of it. Microsoft SQL Server actually has pretty robust support for spatial data types, as does Oracle. SQLite is essentially an extension to the SQLite library that I talked about earlier that supports spatial data types. And H2, I think, is a similar embedded Java-based database technology that I think is really focused on spatial data. And I guess I should point out, Microsoft, the SQL Server and Oracle Spatial are not explicitly supported by Wrangler. All 4 of the others on this list you can run on Wrangler in one mode or another. Yeah, this is kind of what I mentioned already before. These operations that are aware of the spatial nature of the data, being able to do queries based on that awareness, based on these things like, is this point inside this polygon, right? So am I inside the city of Austin? That's the question that spatial database can answer for you very, very quickly and easily, where you would have to do a reasonable amount of coding if you wanted to do this yourself. Certainly more than you would want to if what you're interested in is not just figuring out whether you're in Austin or not. So there's a whole stack associated with these things that typically you're going to use if you want to do things like display maps, work with maps, in addition to just the raw spatial data. You'll want to have these kinds of tools on top of the database. So OGC is just a geospatial international consortium that defines standards around these things. So OGC compliant means it understands standard GIS data as defined by this global organization. And you can have web or desktop clients that may interact either directly with the database or through this GIS server layer. And the GIS server layer may do a couple of different things. There's a map service that actually just produces literally maps. It produces them in a tiled form. So again, if you've used Google Maps, you probably know all about how this works because you've seen the way that it actually will populate the display in terms of tiles. In some cases, you can see how it will resolve individual tiles before it resolves others. So you can kind of see that the tiled nature. Now they'll show an example of different levels of detail with the tiles, but essentially what this is doing is taking in the geospatial data that's stored in your database, translating it into a map image with different kinds of options, and literally producing a PNG or a JPEG kind of file that you can then use to display in a web application or a desktop application. The web feature service is instead giving you the data that constitutes the points and the lines and the polygons. It's actually giving you raw data that you can then use to either build a map or perform other later operations rather than giving you the map itself. So you can think of this like the vector service if the map service is the raster service. Yeah, so here's what the WMS is. You can see it's using URLs in a fairly standard kind of way. You make a request of it, you get a bunch of image tiles. And here's an example of the tiling and multiple levels of resolution. So you can see kind of the coarsest resolution, and then you'll have some kind of most detailed level, and there'll be intermediate versions, and it's going to cache all of these, so it doesn't have to dynamically generate them. If it's already generated them, it'll just give you the ones it's already got. And the same basic thing with the feature service, except what you're getting back is text. And this, to me, this looks like an example of JSON. So there's a few different servers that are typically involved in these things. So the GeoServer and Map Server are open source versions of these. ArcGIS, if you've worked in the GIS space at all, I'm sure you're familiar with ArcGIS. This is essentially got a monopoly on commercial GIS implementations, although the open source implementations have been getting much better in recent years and are pretty good now. And then there's these web clients that use JavaScript typically to consume and display the GIS data within a web application. So these libraries are going to do things like deal with the tiles for you, so you don't have to deal with the tiles. So if you've got a bunch of GIS data, it's now actually relatively easy to get from having a bunch of GIS data to having some kind of web application that actually allows you to dynamically explore that GIS data in a map kind of context. And these layers are really important as well. You know, when you're dealing with tiles, you may not be dealing with just one tile. You may have like background information with the terrain. You may have stratigraphy that lays on top of that, and you may have points that lay on top of that. There's lots of different things that you could put in these layers. You may want to be able to turn individual ones on and off. So again, you can see a lot of the mechanics of something like Google Maps here are directly reflecting the underlying technology. And then there are desktop clients that allow you to do things like editing or more detailed analysis or really, really high resolution images, all of those kinds of things. And there are both open source and commercial examples of these. QGIS is the open source one here, and ArcMap, again, that's part of the ArcGIS suite. Okay, now we've got a few minutes for questions, and we'll also take a break since we're at an hour. So let's try and come back at 2:15, and I'll take any questions.
What's the level of these slides will be on the web page? The slides will be available on the training.
Yeah, they will be posted, right? Okay. And is that on the XSEDE page?
No, but we'll make them available for the XSEDE page as well.
Okay, so there's both a TACC and an XSEDE page. I think they're available on the TACC page now. They will be available on the XSEDE page.
Okay, so it's not out there yet. Because there's training materials right here. You just need to refresh. No, I just didn't. No, are you talking what I'm saying is it's not correct. Oh, I'm saying you need to refresh your browser.
Good. Okay, we're going to go ahead and get started again. I'm going to give a slightly shorter presentation here on some of the specifics of utilizing these database technologies on Wrangler, followed by a couple presentations from my colleagues on loading data into your database and on how to get an allocation on Wrangler. So just a couple of notes here on Wrangler. We have a couple of different models for how you would use a database. As I've already mentioned, there are some applications, things you might think of as compute tasks that really are primarily database processing kinds of tasks. And the data sets are essentially temporary. They're associated with the computational task you want to perform. So in addition to persistent databases, which is the model that you're probably thinking of if you're thinking about having a database, it's a server that's always there, it's always on the network. The database service is always up and available. This is appropriate in the Wrangler context for things like data collections, data that is itself a resource for some research community, stream processing, or things like stream processing where you've got regular additions to a database and you want to continuously be able to perform new analyses or redo certain analyses as the data set is updated. Anything like that where the data set is long-lived and the research needs associated with the data set are also long-lived. In addition to that, we've got a notion of what we call transient databases. Essentially, this is running a database inside a job. And this is particularly applicable to Wrangler because Wrangler will allow you to run jobs for much longer periods of time to allow you to essentially hold resources, including the high-performance flash storage, for long enough that it actually makes sense in some cases to have a job in which you start up a database, and then perform some operations and then shut down the database and shut the job down. SQLite is obviously kind of the simplest possible way to do that, but there are other ways, including using the client-server databases that we've talked about. So again, I just want to emphasize databases as a data collection, as a collective resource, is a valid way to use Wrangler. It's a valid reason to request an allocation on Wrangler. This is a little bit unique in the XSEDE context. We don't have other resources where you can go and say, oh, well, I have this great collection of data that I think a lot of people want to use. I just need some place to host it. Wrangler allows you to do that in a way that other systems really don't. And we really do encourage folks to think about their data and whether their data can constitute an interesting collection of use to the wider community. I also want to highlight that you may have data that is not yet necessarily in the right shape to be a data collection, but could well be. It could be combined with other data. It could form the basis of a data collection. There's a group within XSEDE called ECSS, Extended Collaborative Support Services. They may be able to help you with building kind of the technical armature of that collection. It is, while you can use a database in and of itself as a data collection and just have people directly access the database, it's certainly a lot more user-friendly if you have some kind of a web interface sitting in between it. That could require a little bit of web development at least. ECSS is one mechanism where you may be able to request support to develop such things. And you can certainly always talk to us at TACC about it. I also want to highlight the fact that databases are, often part of these more complex stacks of network data services, like in the GIS example, where you have a server that sits on top of the database and actually provides things like maps. And that this is a really good example of where the Wrangler persistent databases are appropriate. And it may not, Wrangler may or may not be the entirety of the software and hardware stack that you utilize. You could have a website that's actually hosted someplace else. Maybe it lives in the Amazon cloud, or it lives in our cloud, and it just utilizes a database that's sitting on Wrangler, either for capacity or performance reasons. But you know, if all you're doing is kind of a standard LAMP stack and a wiki, and you just want to have your wiki hosted on a database, probably not a good Wrangler allocation. So what do we currently support for persistent databases? I already talked about we support MySQL through the MariaDB fork. This is in version 10 is what they call the one that we have installed. And I mentioned this does include some native GIS data types. And Postgres, we currently support version 9.4.1. I think this is important in Postgres because there have been some pretty big differences between version 8 and 9. And PostGIS version 2 is also supported. And we will have a replication capability to Indiana. That's kind of coming soon. They're still in the process of constructing the whole disk subsystem up at Indiana that will be used for replication there. We're also thinking about MonadDB is one we've looked at pretty seriously to support, and Oracle is at least theoretically possible if we get sufficient user demand. So at least at the moment, the persistent databases live on the disk. The flash is currently treated as more volatile or like scratch storage. It's not necessarily suited for long-term storage. We do intend to provide the flash as an option, but that will have reliability considerations for us, obviously, making sure that the flash subsystem is functioning and is treated as something that stores persistent data, but also for you as a user in terms of the flash is always going to be a precious resource, and there's always going to be pressure to move data through it and to get rid of data off of it if it's not being sufficiently utilized, or if we don't feel like it's making optimal use of the flash storage. And so it is best to think of this as scratch and to have plans for storing it someplace else if you happen to be storing it on the flash. And that's also obviously true of the transient databases I'll talk about in a minute. So all reservations and provisioning of persistent services and Hadoop clusters and all that is done through the Wrangler data portal. I have a screenshot here that shows the screen where you can request a database service in the Wrangler data portal. When this is enabled, it currently isn't, largely because we're just about to shut down Wrangler for the weekend. But when Wrangler is back up and this is enabled, there will be when you log into the Wrangler data portal, you'll have a big Create Database button. You click on the Create Database button and you will get this screen. And what's on this screen? So there's a few options. You have a type of database to select. You may have we may support multiple versions of Postgres if we get sufficient demand. Same thing with Maria. So you'll have a list that includes essentially all of the options that we currently support for persistent databases. You select which one you want. You can give it a name. This will be important because it'll be the name that you use to address it in all your subsequent operations. You can designate a DBA. This is essentially an administrative user who will then have control over who can have what level of access to the database. And an important note here, all the persistent databases use TACC authentication, so you use your TACC username and password to connect to them, but that also means they require that you use the secure sockets layer to connect to them so that you're not giving anyone your TACC username and password. So then a couple of examples of how you would actually connect to these. This is from a Linux or really any Unix system that's got the Postgres and MySQL clients installed. These are the commands that you would issue to connect to the database. So it's pretty simple here. The syntax is fairly similar, and you can see basically there's something that tells it to use SSL, there's a host name, there's a username, and there's a database name. And that's really the important information. And this is going to be common across all of the clients. And that includes the ODBC and JDBC layers. So I already mentioned SAS is a tool that supports databases through the ODBC connector. So you need to be able to configure these. This is going to be an OS-specific and application-specific option. But again, you're talking about the same options. It's a GUI. You're going to have a window. You need a host name, a username, a port, those kinds of things. And all of that information will be in the email that you receive when you've created a database through the interface I just showed you. It'll send you an email and it'll have all that information in it in case you've forgotten. And so basically all of these are going to be for ODBC and JDBC. It's a two-step process. You configure a data source in your ODBC configuration tool, which is at the OS level, and then you basically select the data source in the application. And typically the application is going to have an ODBC connector wizard or tool like that that allows you to basically show and select the data sources. So NoSQL on Wrangler. We're currently not supporting any persistent NoSQL options. That's largely because there are technical challenges to providing most of these tools in a shared persistent service kind of context. As it becomes technically feasible to support them and as demand justifies, we will expand the support for the NoSQL databases as a persistent option. So we really do want to encourage folks, if there is a specific technology that you know you need that really would be best in a persistent kind of context, let us know. You can go through XSEDE through the ticket system, you can go through TACC through the ticket system, or you can just email us directly at data@TACC to let us know that you're interested in something specific. So transient databases. Again, most databases do require a server process, but it doesn't have to be long-lived. It doesn't have to be tied to a node. It can hop around between nodes just like any normal compute task might on a cluster. And pretty much everything that we've run into, everything we've looked at, runs in user space, which means it doesn't require any special permissions. It's not a privileged service that requires you to be root or even have any kind of special privileges. You just need access to the file system like you normally would, access to the network like you normally have. And this is even true of many of the cluster, quote, cluster databases, multi-node databases, things like MongoDB, stuff that's based on Hadoop. So what this essentially means is that you can run a job and you can start up any kind of server process you want within the job, and you can experiment with it, even if the job is a multi-node job, and you can find out if it works for you, or you can get work done with it over the course of the scheduled job. And we do encourage folks to try different things and see how they work for you, particularly if you're in the NoSQL space. So just a reminder, don't run server processes on the login nodes. They will get killed. We have people who watch the login nodes. We have limits enforced. If you have big processes that run for hours at a time, somebody's going to notice and somebody's going to kill them. And it's not going to be a graceful exit for your process, and it just won't be good for anybody. So don't do that. You probably want a reservation simply because it's going to be easier for you to get long-running jobs if you have a reservation. You get a reservation through the user portal in the way you will have seen last week or a couple of weeks ago if you watched the Wrangler tutorial, but it is fairly intuitive. Or you can just start up an interactive job with IDEV. Basically, you do whatever it takes to start the server. In many cases, that's just issuing the name of the binary with a path to where you want it to store the data. In many cases, it's that simple. Sometimes it's not that simple. We will try and provide scripts as kind of we experiment with these, as other users experiment with these, and have scripts that automate the whole setup and launch process. we'll put these in a common location so that it's easy. If you need a Postgres server, you can just start one up from your work directory. So, this is a very, very flexible way of experimenting with databases or getting a database for a finite period of time. And so we do encourage people to do that. Just to point out, you don't have to run your clients in the compute nodes as well. So again, you can start up this server process, and the nodes on Wrangler are all addressable over the internet. They're not on a private network. So you will be able to communicate with them from your desktop if you've opened up a server process on one of these nodes. So you don't have to interact with them from the compute node itself. You can interact with it from your desktop, from a GUI client, from whatever's most convenient to you. Or if you have a job running on another XSEDE system or on a system like Stampede, you may have data that's stored in a database on Wrangler that you need to pull subsets out for a job on Stampede. That's entirely possible. The details of doing that is really going to be application specific, but it's always going to follow a pretty familiar pattern that you saw earlier. You need to know the host name and the username and what database you're connecting to. So just as an example, here's how you would do this for MongoDB. MongoDB is already installed on all of the Wrangler compute nodes, so you don't need to do anything special. You can start up an IDEV session, or you can run a job, and inside the job script you have this command, this MongoD command. This is what starts up the MongoDB process. And I've just shown under DB path, I've kind of shown an example here. This is fictional, but you'll have your own user path on the data file system. It could be the work file system. It could be GPFS Flash to access the Flash. And I'm assuming that you've created this MongoDB directory. And you may want to put this in the background. You may want to just run it in one shell and run the client in another one. And so the second command, the MongoDB name, that's the client. And that's just saying, connect on the local host to the database with this name. If you were running that command on your client, on your desktop, for example, you would also need to pass it the host name of the compute node that you had started the server process on. But that's it. You can see it won't take you any time at all to get a MongoDB process up and running, and you can immediately start experimenting with it. And of course, there are tutorials and such that you can do on the MongoDB web pages. And so particularly for something like this, that you're just starting it up and trying it out, you can put the data on the Flash instead of the /data disk file system that I've shown here. Just be aware that the Flash file systems will be purged. So one note just about Hadoop and these transient databases. Some of these database technologies do run on top of Hadoop. There are lots of different models for how database technologies use Hadoop. Some of them have it kind of integrated in, so that I think MongoDB actually does use Hadoop internally for internode communication, but they don't. The way that they present it is not as something that runs on top of Hadoop. They just kind of incorporate Hadoop into the server process that they deliver, and they give you ways to configure it. But we do have a Hadoop partition on Wrangler, and so you can get a reservation on the Hadoop partition in the same way that you would for a regular job. It will set up a Hadoop cluster for you, and you can then launch your database as a Hadoop application, again, just as you normally would with any other Hadoop application. And then you'll have your server process up and running, just like with the Mongo example. The note I want to make here is Hadoop obviously is a fairly complex distributed system. So if what you're doing is tightly integrated with Hadoop or really dependent on the Hadoop internals, you probably want to be familiar with Hadoop and how it functions as well. So just kind of a warning there. It can get complex. So just a note on performance expectations. So I think, particularly if you're running a transient database on the Flash, you should generally expect something like 2 to 3 times the performance of what you would get on a typical disk-based host. And this is not necessarily a linear relationship to how much faster the flash is than disk. There's lots of other factors as well. And if you're really interested in performance, then you probably will want to spend some time tuning your database server parameters. There's lots of different ways that it can handle, particularly things like buffering of indexes or in the case of Postgres, how it actually plans and executes queries. You can get really fine-grained control over those kinds of things. You may want to get into that. You certainly want to get into how it executes I/O and how much buffering it does if you've got large data sets, and that's important to you. There's enough memory on the compute nodes that it's conceivable that all of the important data in your database can be buffered in memory, and you should certainly do that if it's possible to do it. In that case, you'll get much more than a 2 or 3 times improvement over a disk-based system. Yeah, so the more of the total data set you're accessing, the better comparative performance you'll get. Essentially what this means is the more time you're spending doing I/O, that is reading and writing data, the bigger an impact the flash is going to have in performance. So just a couple of notes here about staging data. You can load up your database, load your data into your database directly from your desktop, your laptop, another cluster. Network performance may be an issue if that's what you're doing, and there's different ways to stage your data into your database that may be more or less efficient. So certainly something to consider or ideally probably do is to stage your data to Wrangler before you're going to load it up. And you might want to just put it on the flash temporarily as an input data set, pull it into your database, and then just delete it off the flash. But you don't have to. Again, this is something you may want to experiment with. You may also want to consider preparing your data. This is something David is going to talk about in much more detail right after me. There are ways that you can transform your data ahead of time so that it directly can be loaded into the database as, for example, a collection of rows that are already formatted the way that your table is formatted, and the database can optimally pull the data in. So just kind of, for example, I showed you the insert statement before. If you have to load 10,000 rows, you can either model that as 10,000 insert statements or as one insert statement with all 10,000 rows in it. And you can probably guess which one is going to be faster. Staging data out, again, it's just important. A transient database is transient. It goes away. Your data will eventually go away if it's on the flash. We're not going to delete data off the disk as long as you have an allocation on Wrangler, but the flash is going to get purged. And you may need the server process running to pull your data out. That's not necessarily the case. You can just copy the raw database files, but you're still going to need the server process at some point to make some sense out of that in almost all cases. So you do need to think about if I have important data in the database, how do I pull that out before my job is over, before I'm done working? What's the most valuable format, or what formats do I need it in, and how do I get it out in those formats? But you can also use these database dump and kind of backup tools. There's simple tools from MySQL and Postgres that just say dump all of the raw contents of the database, and that's in a form that you can then just feed right back into a MySQL or Postgres database, and just essentially kind of dehydrating and rehydrating the database. So what you want to do is use Wrangler to build a complex data set as a database that you then might run over the long term someplace else. This would be the best way to do that, or just to have a copy of it in case you find that you need it later on. The important point here is you do need to think about that and be prepared for it. And I can quickly take any questions before we move on to the ETL presentation. Okay, David Walling will now take over the presentation.
Thanks, Chris.
So my name's David. I work with Chris and Niall in the data group. In my time at TACC, I've had a lot of experience working with databases and pretty much all of the contexts that Chris had described earlier. Actually working with research databases, working with databases that we've developed to run our web front ends, essentially. And a lot of my time has been spent doing what's called ETL processing. So ETL stands for extract, transform, and load. And the whole motivation is that you're going to get access to data in a variety of usually unwieldy formats. And the idea is to get all of those into a single place where you can start asking questions across those data sets. And a database is a very good tool for doing this. But it's not always as easy to just take the data and dump it in a database. In fact, 80% of the effort is usually spent in actually cleaning that data up and putting it into a format that you can actually then load into a table. So let's see here. More often than not, you're going to get some kind of CSV style dump of the data to work with. Though there are cases where we've seen where you actually have scripts that will just say go out and scrape data off of a particular web page. And then you may have very funky formats like this genome type data here. In all cases, you're going to have to essentially write scripts to clean that up for you. And in that process, it gives you an opportunity to deal with a lot of the badness, essentially, of the data. So kind of common things that you would do to transform the data is to take things like your text string and to map that to another table. So in this case, I may have a table that lists all the states that I'm interested in. And when I pull in a new data set that has TX as one of the fields, I actually want to map that to the foreign key in that table so that I can directly enforce constraints on my data so that I can't ever have a record in my data table that's pointing to a state that doesn't exist, for instance. It gives you an opportunity to put data into a different data type that's going to be easier to deal with. So one example we'll look at is if you're getting information, let's say, on height, so basketball players. It's not very easy to use 5 foot 10 inches in a lot of computations. You actually want to convert that into something like inches, which is going to be a lot easier to aggregate to do calculations on. So this is kind of the natural place where that happens. And then another big one is dealing with missing data. And there's all types of different codes, esoteric codes that people may be using to represent those missing data. Generally what you want to do is to transform those into something consistent across all of your data sets. Once you've cleaned it up, of course, you then want to load it somewhere where you can use it. And in this case, we're focusing on databases as that backend. Although that doesn't necessarily have to be the case. I mean, it could be you're just dumping it back into another CSV file or some other type of database backend that's not necessarily an RDBMS system. So what are the tools that we typically see and use for doing this? The first is people usually when they first get access to a data set, they start kind of cleaning it up manually. And that's fine, that works okay, especially for smaller data sets. But eventually you're going to hit a point where doing it manually is just no longer really feasible. Basically, if you have to do it more than twice, then you need to start thinking about scripting it up. The scripting tools that are generally used are, the first set is just your basic Unix tools. A lot of people who are coming from a Windows world over to Linux aren't necessarily comfortable with these at first, but the truth is they're extremely powerful. There's a very nice way of gluing all these individual tools together to do some very powerful things. And generally speaking, they're extremely efficient at what they do. So they can handle very large CSV text files, for instance. And I'll show a couple of examples of those later. At a little higher level, you have your more full-featured scripting languages, such as R, Python, and Perl. And I'll talk about those in a little bit more detail. And then at the highest level, you actually have GUI-based tools that allow you to build these ETL pipelines through kind of a user interface. For people who aren't as comfortable working at the bash level or even in R or Python or something, these can be really good options for you. And I'll show you what those kind of look like. Here's a typical example of what you would see, right? So here we have some data, which is information on basketball players, their height, weight, position that they play, and a grade from a scouting agency. So the first thing you might notice is that you're going to have fields such as NA, where data is just completely missing for a particular record that you're going to have to deal with, essentially. You also may have things just like bad data. So in this case, scout grade ranges from 1 to 5, but here you have a record where it's at 6. So you need to somehow build in business logic to your ETL processes to kind of clean that up to make it usable. And then again, you see that, well, I know what this means just looking at it, 5'11", but that's going to be very hard to use in code. So I'm going to change the format of that information into something more usable. So if we were doing this through Unix command lines, what does that kind of look like? So I kind of already touched on this. The major pro to this is it's extremely powerful and extremely efficient, fast, essentially. The big con to it is quite difficult to learn. Fortunately, there is a lot of examples out there on the web of how to do stuff. So if I need to say, oh, how do I print the 3rd and 7th column using awk on a Linux? You just Google that, you're going to get tons of examples of how to do that. So you don't have to memorize everything, but it's definitely a little bit daunting at first to kind of jump into that pool, but it's worth it. So in addition to things like awk, you have things like grep, find, cat, let. I mean, these are your just basic things that when you're working on a Linux system like Wrangler, that you will at least want to be familiar with. Even if you don't end up writing your full ETL pipeline in these tools, they at least help you explore new data sets that you get to start doing things like, well, just show me the first 4 lines of a 150 gigabyte CSV file, so I can kind of see what the format of that data is. These are just kind of, there's probably a lot that I don't even know about, but these are the ones that are the most common that I use pretty much on a daily basis for different things. Awk and SED are again very esoteric really in the syntax that they use, but extremely powerful. And then some are a little more straightforward, like sort, unique, so on and so forth. But here's an example of basically piping together, how you would pipe these together on the Linux command line. So here I'm basically printing out the position of each player in my data file, and then I'm going to sort those entries and then only return the list of unique entries. So that even if this was a 250 gigabyte file, this command would run relatively quickly and show me all of the unique values I have for a particular column. Even loading that into something like R, another process, you may not be able to do because they're going to try to load it completely into memory. This does allow you to do things like that. I'm not going to harp on regular expressions too much, but I did want to make sure you're familiar with them because they're pretty much ubiquitous. SQL queries essentially allow you to do regular expressions. All of these, Perl, Python, all of these Unix commands essentially can work with regular expressions. And basically they allow you to create very sophisticated ways of finding information. So if I need to look for all zip codes of a particular format, and that's the only data I care about in this huge data file, you can write very powerful regular expressions to go through and locate that information in the file. Again, fortunately, because the syntax for it is not intuitive at all, but there's a lot of good resources out there to help you build exactly what is the regular expression you're looking for. A very common use case for that is if you have dumps of like web events essentially, and you only care about URLs essentially that match a certain pattern. This is kind of how you would go about doing that. And again, you pretty much see these everywhere. There's for the most part, there's some consistency, but everybody does a couple of things slightly differently. So just kind of be aware of that as you start to figure out, well, how should I do this regular expression in Postgres versus Python or Perl or something. At the slightly higher level, you have the things like Perl and Python. Most of these provide ways of just doing standard in, standard out, kind of very similar to like piping information between different low-level command line tools. But one of the big advantages of writing things in Perl and Python is that these are full-fledged languages. So basically all of the investment that you put into developing your ETL scripts and learning that language, you can be used towards other things. I mean, Python and Perl as well, you could write an entire web application in the same language, right? So you can go from processing your data to putting a front end on it, all within a common environment. There are issues you will start to face, things like trying to load a file into memory within one of these tools. If the file's too large, you're not going to be able to do it. But I write most of my ETL code nowadays in Python, and I highly recommend it. Perl used to be very, very common. One of the reasons was it was always installed with the Linux distributions. It's become notorious for being extremely difficult to read. People try to write their Perl scripts essentially in as few characters as possible, which makes it impossible to understand what's going on. It's becoming less and less popular, but it is still out there, and it is definitely very fast. I mean, it's basically on the level of your Unix commands, essentially. Python, partly because I think people hated reading Perl code, is all based around making the syntax easily readable. It's been growing in popularity. It's the one I use the most these days, and I highly recommend it. It can be, there is definitely some overhead to learning it and kind of getting to be productive with it. But once you are, again, it's very powerful. You can do, there's so much available that you can do in there. One of the big things about Python, and Perl has this as well, but you get access to third-party packages or modules that aren't necessarily in the core Python distribution. But essentially, the same thing with R. If you need to do something, 99.9% of the time somebody else has already done it, and you can just go reuse their code. Saves you a lot of time, lets you concentrate on your research. Then at the kind of the highest level, the easiest for a non-programmer to start working with are these GUI interfaces. The really nice thing about, and I'll just kind of skip ahead to the screenshots, the two ones that I've used the most in the past is SQL Server has their implementation of this called SSIS. I used to use that quite a bit back in the day. I've moved on to using what's called Pentaho Kettle, which is a very similar product, but completely open source. It's basically Java-based. It's had a lot of active development in the last 5 years and it's become quite powerful. And it basically looks like this. You literally drag and drop different tasks, connect them up with arrows, configure inputs and outputs, and it's nice that it's very clear for somebody to come in and see what your code is doing, right? They can just kind of follow the workflow. And as you're actually running the code, it'll actually have counters showing you how many records go down each path and things like that. The disadvantage with doing something like this or using one of these tools is that you're essentially only learning how to use that tool. Whereas with Python, you're learning Python and you can use that for so many other things. All this will ever do is run your ETL scripts, essentially. I do recommend Pentaho Kettle, though. It was a very pleasant experience working with it when I did a couple of projects in it to essentially grab information off of websites and pull it down for some energy research. And it's also processing a bunch of daily CSV dumps that we were getting. It's actually quite, even though it's written in Java, it's actually quite fast as well. I think we could process like 50,000 records a second or something like that at one point. So it's pretty powerful and you can pretty much run it anywhere. Once you develop these scripts, whatever language, whatever tool you decided to use, it's very common with databases and really any kind of data workflow to run these scripts on a periodic scheduled basis. The main way to do that on Linux systems is to set up a cron job. This is, essentially a scheduled task that should run on a periodic basis. So here's a couple of examples for some ETLs we've set up, again, for research that we're doing here at TACC. The example of syntax is simply this. So at 3 a.m. every single morning, go out and execute this bash script. All that bash script really does is fires off the Pentaho Kettle process, essentially, and specifies where to log everything that happens in it. We are going to support cron jobs on Wrangler. This is very different than any of our other systems. We're still trying to figure out the best way to do that, since it is a little more difficult to do that in a multi-tenant environment. You certainly can't run the cron jobs on the login node, because that would use up just the same reason you can't run a database on the login node, is it would affect all the other users. But if this is something that you need for your research project, come talk to us so we can discuss how to best set that up. Because that's something we do want to support on this system. We wanted to talk a little bit about streaming. By streaming, we mean that essentially you have a daemon, a process running somewhere that can always accept data coming from a source and process it and, say, stick it into a database. A lot of companies are essentially doing this now, and like 90% of the workload is processing the log files coming from their IT resources. All of these web startup places have kind of gone to the philosophy of log every single thing that happens on our systems. And what that allows you to do is not only, when your application breaks, it allows you to go figure out what happened, but probably even more powerful is it gives you really powerful business intelligence on what your users are doing, right? So because of that, there's been a lot of really good products such as Apache Flume, Loggly, Logstash, and Splunk that can handle this type of continuous data flow workload. They're all geared towards making the turnaround time of an event happening and you knowing about it as small as possible. I'm a little skeptical if we'll ever need that type of performance for research data workflows. But if you do, if that's something you think you need, then again, come talk to us so we can look at setting that up. I mean, one area where I have seen this before is that it may be the case that the data that's being generated, maybe from a sensor out in the field, is only available for a very short amount of time, and then it gets overwritten because there's only so much, essentially, storage capacity on those sensors. So we have set up processes like this in the past where you have a constant daemon always available that those little sensors essentially can talk to and report their data to. Again, talk to us if that's something you think you need in your workflows. Finally, I'll just kind of touch briefly on, once you get all your data cleaned up and put into your database, how do you actually use it? Chris already covered some of this, but I'll just show a few examples of, connecting to the database from common analysis tools that we use here at TACC. Basically, SQL is used everywhere. All major analytic tools, SAS, R, Python, so on and so forth, utilize it. But every package, of course, has their own slightly different way of doing it. So I won't go into too much detail about how to do that for any one, because I have no idea what you guys are interested in. But almost all of them follow the same type of pattern, right? You manually open up a connection in your application. You, through that connection, send SQL statements. And then the client is responsible for packaging up those results and returning it to you, usually in like an array or list or R data frame, so on and so forth. And then at the end of all your scripting and analysis, depending on what you're using, you need to manually close that connection to clean it up. Here's just a couple of examples. So here is using the JDBC interface to connect to a database from R. You essentially install this third-party package from CRAN. You need to get the MySQL, in this case we're connecting to a MySQL server, so you need the MySQL JDBC driver, essentially. Just register that, enter your connection information, very similar to what Chris was showing. That gives you a connection object, which you can then pass to these sub-methods to kind of start exploring your database. What's nice about these packages is it does save you from having to write certain SQL statements yourself. So instead of having to write select all from mysql.schemas.table or table name like, blah, 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 it just exposes a single method, DB list tables, which gives you the same information. There's hundreds of these though, so usually you let the community tell you which one's the best. So connect to database from R is going to return you the most popular CRAN packages that people are doing this with. Further examples of higher level interfaces for doing things like writing data to a table or reading data back out of the table into a data frame. You don't have to memorize all of the SQL commands to doing that. These abstract that away for you. This is an example in Python where I'm connecting to a Postgres database. So very similar type of workflow. In this case, I've simply encapsulated some of the steps into sub-methods. In this case, I'm using a Postgres-specific driver, which actually I would not recommend. Usually, you have this option of going over JDBC, ODBC, which Chris covered, or using a kind of database-specific driver. In almost all cases, you want to use that open driver because it makes your code portable. You could very easily switch between MySQL, Postgres, whatever. Your code doesn't have to change at all. You just change that connection string. In the cases where you may not want to do that is that those database-specific drivers may expose functionality that only that database exists, and maybe you're really interested in using that. And then in some cases, there is some overhead to having database agnostic drivers. So if you're really worried about performance, you may look at using the database-specific drivers. So that's kind of why we did that here in the Postgres example. But same type of situation, when you're ready to query something, you just create a connection to the database, open up a cursor, pass it in some SQL, which here's an example of doing that, and it'll execute that SQL, package up the results, and return it in a list, I believe, in Python's case. And that's really it. Again, I don't want to show too many examples because it's really going to be specific to whatever your application is doing as far as how you do this. But the main takeaway I would have from this is that if you're manually doing something over and over again, think about how to script it up. We have a lot of additional trainings on things like C, Python, and R. If you're not really comfortable doing that yet, we can help you out there as well. But eventually, you're going to save yourself a lot of time by setting these up as scripts and letting the computers work for you. And finally, I think Niall will talk about how to actually get your allocation set up on Wrangler. So thank you.
Can I ask a question?
Yes, sorry,
Because
question.
I don't know. What version of Python are running on Wrangler?
79.
7.9.
Very good question.
Yes.
Rarely.
Would you support both?
I built it for somebody on Maverick, for example, and I think there was resistance to supporting Python 3 because there was less adoption amongst many of the common packages, in particular NumPy and SciPy, and so we sort of shunned away from it then. I think that's becoming less the case, and so it may be time for us to review that again. My concern, though, is when you don't have backwards compatibility, supporting something that somebody might use accidentally will lead to great frustrations. And so,
I'm just curious if at some point
well, it's not clear. They said, how long has it been Python 2 and Python 3? So,
Three may die.
so
and 4 may resurrect with 2 months. So
yeah,
I didn't know that.
yeah, there've been rumors on that for a while. So, and who knows? Perl make a huge comeback. No, it's not going to happen. Not going to happen. No.
No, I've got a couple. To me, all I've spent is learning how to do tricks.
Yeah.
Yeah,
Perl is one of the more
basically.
expressive languages, which is what my wife loves about it, because it's more, she says it's more like literature. You write what you're thinking. The great debate over whether Perl needed the don't statement to fill out its verbiage was sort of an interesting piece of computer science. But that's sort of a little digression there.
Now, sir, I got a couple quick questions. The first one, you alluded how David, you alluded how Perl was pretty fast. How does Python compare? And the reason I ask this is I'm with the CSR and the Grace follow-on mission, and we're going to use Python, it's been handed down from on high that our language for encoding stuff, or storing, putting stuff, jamming stuff into the database for us is going to be Perl. And before that, we've used other languages, some of it Python.
Mm-hmm.
I said Perl,
Yes.
I meant Python.
Right.
I've not been impressed with some of these interpreted languages. My concern is that Python is going to be a bottleneck with the amount of data that we're jamming.
There's communities that are very passionate about looking at performance and how to compare performance between things like Lisp and Python and Perl. I haven't seen really any, especially for these like ETL type processing, where Python has been a bottleneck for us. I suspect Perl could be faster just from a pure CPU crunching data numbers. But the other aspect to that is how much time do you end up maintaining the code, because it's difficult to read. I mean, Perl's a beautiful language. It's just a lot of people have gotten into the habits of making it obfuscated, so you don't really know what's going on with it, right? It's
Can I compile? Is there a compiled version of Python? Okay.
Yeah, I mean, it's interpreted. I mean, you do get PyC files which optimize things. And so once you run it, they do some optimization on it above and beyond what you wrote, but it's still interpreted, and it's still coming down to some interpreter similar to Java. It may not be compiled down to bytecode, but you're never going to have a scripting language that's as fast as a compiled language, and that's why we still, half the jobs on Stampede are running Fortran, a language that you talk to most people and they laugh about, and yet it's still one of the most powerful engines out there. Yeah, exactly. So,
everything else out
yeah, but we have worked to try and optimize at least portions of the Python interpreters. And so one thing, I don't think we run any tests against for doing text processing and ETL sort of things. But we did find that, for example, compiling Python against the Intel compilers as opposed to the GCC compilers, we got a significant speed up because the compiler was better. And similarly, the same thing for Fortran code. If you compile it with the Fortran compiler from Intel for that chip, it's going to go faster because it will take advantage of all the tricks that it can. Might be an interesting thing for us to look at and see. The ones that we have installed on Wrangler will be, the Python we have is all Intel compiled and MKL, then all the magic bells and whistles are thrown in that we know of. So it might be an interesting test just to see that. I agree somewhat with David. The supportability I find more important than the speed often on these things. When I was working at Hubble, we migrated everything pretty much over to Python from a lot of Java.
But if we wanted the most speed for the ETL, I assume we just use C.
Well, so what's going to happen is, and what's nice about Python and R as well, is that there probably will be one point in your code that is the major bottleneck. And you have the option with Python to just writing that portion in C and then just wrapping it basically from your Python. So you have all the easy maintainability of your Python workflows, and then you just write that one part in C to achieve maximum performance.
My second question, I'm sorry for this delay,
No,
is the other strand. What I've just talked about is the production.
Mm-hmm.
Then there's another line where it's not so much putting stuff in databases, it's querying stuff out to the extent that I understand databases. And you mentioned the Pentaho kettle. And I was first surprised when you put a call to that, the Pentaho kettle under a cron job. So you can actually build a script that you don't have to invoke it graphically or manually.
That's correct.
Okay. What my question is either Pentaho or is there a class of these type of ETL type of things that you could, for our analysts, they could build an analysis protocol or workflow. It will spit out Java code or something, and then we can go in and tune that or update it. Is there anything that that is basically
you're looking for a visual editor?
like a compiler,
yeah,
rewriter.
Yeah, so most of these tools actually work that way. And most of these steps, this one happens to be Java, but a lot of these are actually running like JavaScript under the hood. So all they really do is essentially exactly what you're talking about.
Yeah, but what, can I save the JavaScript and then go in and then tweak the JavaScript?
Yes, essentially you can. And these things have full support of parameterizing all of these workflows so that when you call it from the command line, you just pass in different parameters and it'll behave accordingly to how you set that.
And the reason I'm saying it this way is that we may have an analyst that wants to build some database interface, and they want to build it first graphically, then use that graphical interface to basically build a script, and then we can tune that script, you know, if it's too slow or something like that. So he's building a workflow using a GUI as a first iteration of building it, as opposed to just building it directly either Python or Unix.
I mean, in that case, Pentaho Kettle, basically how it saves its workflow is in a big XML file with all the different steps. So that would be kind of clumsy to work with and just go in there and directly edit to do what you're talking about. I will say that there's a huge business around this now. So there's companies like Informatica.
But I don't want to pay coin.
Exactly, exactly. So,
well, but to me, it sounds like, I mean, it's a lot like many of these visual editors that everybody wanted to push for how you develop code.
Right.
And every time I've done that, every time I've used a visual editor, I last about 15 minutes, but that's just because I want to see the code. But most people will last, you know, a little while, and then they'll hit that stumbling block, and they'll have to go and learn it. And it's how well that exposes things out. So there are different ones out there for different languages. I don't know any for ETL in particular that can do, you know, produce pretty code basically, because all of those languages that I'm thinking about produced compilable code, but it was not readable, you know.
yeah, I agree.
And that's usually the thing, is to try and get as much optimization out of the visual portion. They take it's not human readable, not as human editable, the code.
Okay.
So that's been my problems with all of those in the past, and maybe there are a few out there, but
I ask only, that's my impression, and my context with it is like, you know, Word, Microsoft Word, you write HTML. It's God's awfulest HTML code.
exactly.
Okay, and no human would ever write anything like that.
Yeah.
But it wasn't. But I didn't know if the state of the art had progressed past that disaster.
I haven't seen it yet,
Okay.
and you know, I think it's just, in the end, it winds up, it's why you still use VI and Emacs. It's, you know, often once you're really in the nuts and bolts of it, that's where you need to be. Now, a lot of people will do ETL cleaning in something like Excel. You know, you can do that, but I don't think that things are exportable out of that into a batch environment. I think there's that give and take.
Under your Linux cores and work on 2 GB size files.
But can't run Excel under Linux.
Oh, okay.
You know.
And it's not an option.
Yeah,
for us.
yeah, exactly. So, you know, that's.
Okay. Thank you.
So I'll go very quickly through this. For folks who have already had allocations, a lot of this is sort of going to be old hat. I'm Niall Gaffney. I'm Director for Data Computing here at TACC, and so I get to give the not so technical portions of all these things because I work more in bureaucracy. So the Wrangler allocation model is a little different, though, from what most people are used to if you've been using XSEDE or TACC-based resources. Up to this point, we've largely been a computational house. We haven't been a data house as much. We do have some storage allocations, but we haven't had a data analytics machine like this before. And because of that, we had to sort of split things up a little bit to really allocate this system appropriately. Wrangler will have 2 different things that you can allocate. You can allocate compute, and by compute, we mean time using the computational system, including use of that flash storage system, which is part of the computation engine in the way we think about things. Or you can, well, not or, and you can request storage allocations. And storage allocation is for this long-term spinning disk type storage, which you can use for depositing data in, storing data in between your computational jobs, so dumping databases out of, reading databases back into, and these sort of ethereal or transient databases as we've been talking about, as well as where you can store your results and data and information that you want to share with your peers or preserve in the long term once you've actually come up with all the brilliant results that are going to come out of the system. Because Wrangler has this computation concept that's slightly different from a lot of other systems, and because it's more complex, sort of merging some sort of high-speed storage with a high-speed computation system, and really the magic here is in putting those two together, we came up with a notion that's somewhat different from how, at least in XSEDE, we've done allocations till now. And the notion of that is, rather than allocating things according to how many cores you're going to be using, which was sort of, for a computation made sense, for doing data analysis, because the flash is there and because of many other things are sort of limiting things, we wanted to get away from that notion of cores and just go to what you can do with a particular node. And so the node hour is what we talk about here. We'll interchange it with what we talk with the service unit in Wrangler, the same thing. But we tend to think about things now as a node hour. And a node hour gets you one node of computation power on Wrangler, which includes basically the two CPUs, which have, each of those CPUs have 12 cores, so 24 total cores. We'll mention we are hyper-threading enabled on Wrangler, so it actually appears as 48 cores. And for some things, we're finding that having hyper-threaded cores is really helping out, especially with I/O bottlenecks. So we've left that turned on. So again, it really is because we're presenting the system somewhat differently that we've gone away from this. We're talking about node hours, but it gives you those two CPUs, gives you 128 gigabytes of memory of real memory where the CPU is working what you're used to. Plus, it gives you then an allocation of 4 terabytes on the flash storage system for you to use throughout the duration of your job or reservation. And so you need to sort of think about what the limiting factor of what you're going to be doing on Wrangler is to figure out how many node hours you need. Whether you're limited by the amount of flash storage you need to have, say 40 terabytes of flash storage, you're going to need to ask for 10 node hours, even if you're only going to be using computationally, say 4 CPUs worth. So you need to sort of balance that out, and rather than go through math, I think most people can figure out how to do that. But it's sort of a balancing of what's limiting your job, and it may be number of people working on things simultaneously. If you have a particular lab that's running through and needs 4 nodes for people to be doing data analysis on, well then you should ask for 4 node hours per hour. For dedicated databases, we want to have a nominal charge as well, because we really, we are supporting computationally what's going on with the database. And so we want to charge a bit for that shared resource. So we came up with the notion of just one node hour per day for these shared resources. And that basically translates to having about 150 gigabytes of database on the flash memory for the period of that. Or you can have that then for that, or for larger databases, or ones that don't require the high transaction rates that you can get through the flash memory, being able to host those on the spinning disk system. And so if you need that, you can request a storage allocation in addition to your computational allocation, merge those together and go off and use that. And I think we may have mentioned this, but I wanted to sort of stress on this. If you are doing sort of flash-based storage of databases, or even if you're doing storage of databases on the disk system, it's a good idea to go ahead and back up those databases periodically, just because it's often, well, bad things happen. You can never tell. In computers, we're all used to that. But in particular with the flash storage, because the flash storage is not replicated between here and Indiana, as we are doing with the disk-based storage, there's not a second copy of your data. So it's a good idea to keep backups. For transient databases, you sort of should think about, getting 1 node hour per hour if you're going to need 1 node to sort of stand up a database, unless you're sharding or doing some other things. Unless, of course, you're working with larger than 4 terabytes worth of data on the flash storage for doing your extract, translate, loading of the databases, for hosting the databases and extracting your results. So typically that's where you would go, but you may need more depending on your situation. For actually going and getting an allocation, best place to start is at the XSEDE portal. You can log into the XSEDE portal at portal.xsede.org. There you can click on, get an account. If you don't already have one, and come into this handy dandy form here where we'll get some information from you, and somewhere down below is a simple enough CAPTCHA to fill out so that we can determine that you're not a bot and all those sort of things. It'll vet through, make sure your email address is correct, and then come back with a valid account. Once you have that, you can then come in. You can click on that sign in button on the upper right hand corner, sign in, log into the portal. Once you log into the portal, it gives you a nice sort of status overview of what's going on and what your account's doing. To get an allocation, go up to the allocation tab, and then you can sort of read up then there from the overview as to what goes into getting an XSEDE allocation, overall philosophy of what should go in different fields in the actual application process. But for sort of just getting going the first time, getting started or kicking the tires here on Wrangler, we encourage folks to use sort of the startup allocations, and there's details about startup allocations on this form here as well that you can read up on. But really and truly what I wanted to say here is that for startup allocations, it's sort of a minimal amount of information. We'd sort of like to know that what you're doing, so maybe we can help or make sure that the right packages are installed or whatever. And then, some justification as to, how big your startup is going to be. Nominally, startups are probably for between 500 and 1,000 node hours and some terabytes of data. And so in general, as long as you say, I'm doing something cool with databases and I need to kick the tires in this way, and I want to stand up something for a few days to play with this to demonstrate that it's going to work for me before I go off and get my huge allocation, you fill out the forms and you can get one fairly quickly in that way. To sort of actually submit the allocation, you click on the Allocations tab and go to the Submit Renewal or Review Renewal tab that pops up underneath it, and that takes you into a form here that shows you the different available opportunities. Allocations in XSEDE for larger allocations are accepted 4 times a year, normally in, I think, month-long windows. And when those windows are actually open, you would see then on this form that general opportunities or proposals are available. In the interim, such as the time that I took this particular screenshot, you see that sort of the campus champions and educational ones are available. And then below that is listed the startups, where if you're eligible to have a startup, meaning you're not a PI or working on other projects, you can go click on that and ask for a startup. If you need a startup and you are already PIing on other things, get in touch with us and we will get one set up for you. It's a new enough system and a different enough system that I think the current thought behind a startup should only go to people the beginning of their particular research doesn't quite make sense. We want to get more people on this different sort of resource, and so we'll work with you on that. Once you get done clicking on that, there's sort of a nice handy form that'll start taking you through the process of what to fill out. And again, we don't expect in a startup allocation great detail. We don't need to have scaling plots or any of that sort of stuff to show what you're doing. We just want to get a good feel that what you're doing on here is sort of applicable, and that Wrangler is indeed a good place, given its limited resources, for you to come in and start doing some things. Leads you through the process, and then you click submit. It winds up in my inbox probably within 24 hours, and I will then say, yeah, go for it very soon thereafter. There's sort of the information. I think I covered most of this while I was going through this, but saying it's like I need a database to study something like this would be the one sentence sort of justification for why you need to work with Wrangler here. And I guess that takes us to the end of the presentations. So I will pop this back up like this and ask if there are any more questions or further discussions, or I guess let folks out in chat land finish catching up and go from there. Well, power goes out soon enough, so.
Chris touched on it a little bit, but you want to emphasize that actually after you get your allocation awarded through XSEDE, that you would come in through the Wrangler data.
Yeah, we didn't show that as much, and so we should probably reiterate that. Once you come in and get an allocation, the XSEDE portal will also be the place that you can go to add other people to that allocation. Everybody on Wrangler will need an allocation within XSEDE. Because of the multi-site nature of it, because it's here in Indiana, we need to have a global sort of account to track through. But once you can go in there and you can add more people to the project, get everything going, set people up as delegates, just like you do with every other sort of XSEDE allocation. But then when you need to actually start standing up services and reservations and all those things, the Wrangler data portal, which we should have linked in with on the sites, but if not, is portal.wrangler.tac.utexas.edu and is featured very early on in the documentation that we have for Wrangler Online, both at the XSEDE website and at the TACC website. Will lead you to that site where you can log in, where you can make requests for databases, where you can make requests for storage allocations and for compute resources. If you have any issues with that, the ticketing systems at both XSEDE and TACC are available. You can, please get in touch with those. If you're not able to do something that we haven't thought about or that you need in addition to what we've done so far, please contact us through those sites as well. Or if you feel like it, you can also email us at data@tac.utexas.edu. That'll wind up in everybody's inbox, in my group at least, and we will get to that. Typically, we'll file a ticket on your behalf so that we can track through issues and problems, but we also do respond to that. Sure, I could do that real quick. All right, so we had a request to sort of show the portal, so I just get nervous with live demos.
Well, it was just done there. It seemed really good.
So you come in here to portal.tac.utexas.edu. You can click on login. We accept either your TACC or your XSEDE portal accounts. At some point, we'll have the Indiana ones as well in here because there will be three different methods or ways that you can log into the different parts of the system. Log in. It will take you to a dashboard at the beginning here that shows you what projects you're on. You can get details about those projects, showing who has accounts in those projects. All of those have been added through the XSEDE website. You can expand each one of these, or you can go in and manage a particular one. And when you come in to manage something, you'll see sort of a list of pending reservations that are up here. So I have a reservation that's scheduled to start tomorrow at midnight here that hasn't started yet. You also see a list of all the pending past reservations that have gone in the past. You can expand on these so that you can then see what happened to it, what it was on, and what the start time was and the finish time. But for what we're dealing with here, database services are up here on the right. We don't have a I apparently don't have the on this particular project. I don't have the button here to create a database because I am not the leader of this particular project. Were I would be able to do that. There's also a button here to be able to create the IRODS collections, which are storage collections for folks. Let me go to a different one where I might have a database. Come here to the dashboard, and maybe I can come into this one.
We have that turned off right now.
Oh, okay. So we have that turned off right now. There's an issue with it. They're telling me this is always the problem with live demos. But once you get in there, we will be able to have a button in the database services, which will lead you to a form somewhat similar to this, which will ask you a few questions about what you need and allow you to say, what sort of database service you need in the dedicated services and how big it's going to be and what it's going to be named and who's going to manage it for you in there. The other interesting things here is the user profile allows you to come in and see, your name and email address, which if you've forgotten, that'll help. But it also lets you know all the other things that you may have forgotten, such as your username within XSEDE, your username within TACC, and then certain paths that are important paths to you on the system. We will continue to augment the user profile with more information as people need things as we find it appropriate. And so if there are pieces of information that you would find useful about your account that should be in here, let us know and we'll get that on there. In addition, there's documentation available so you can get an overview of the system. You can go straight to the user guide here and the Wrangler user guide to get more understanding. of what's going on and how it works. And there is that particular link I was saying to portal.wrangler.tac.utexas.edu at the top of the user guide that you should be able to find to get where we were just a moment ago. So watching somebody else surf the web is always one of the most exciting things on a Friday afternoon. And so with that, I will leave my web surfing to fade away as it should. And I hope that helps everybody understand how to work with Wrangler a little better. We want to have more of these sessions in the near future. We'd like to have some sessions about the Hadoop capabilities. Again, more sort of illustrating what's possible on Wrangler and what we can do. And then coming up probably this summer, partially at XSEDE 15, but also we'd like to have some other sessions as the system is being used and is in production. We'd like to get some folks on and start doing some more hands-on sessions where we might actually, have projects which involve a few databases for people to come in, do some things, understand some of the tools that we've been talking about and how to put things together. Similarly for Hadoop or for R or for a lot of the other sort of environments that we are using on Wrangler to push forward how to curate data and iRods and how to share things with colleagues. All of these things are some topics that we want to both talk about and get people some exposure in. So we look forward to those in the summer, and we would also really encourage people to fill out. There will be a SurveyMonkey survey that will be coming out on the tail of this. But also, please, feel free to email me directly. You can find my email on the TACC website, email data@tac.utexas.edu, or any of your friends and colleagues here at TACC with ideas and suggestions as to what in particular, what features of Wrangler you would like to see covered to get you going on this new system in the near future. We will really want to react to what people need and not just be sort of talking heads up here trying to cover what we think people need. So please let us know on any of those forums what we need to cover and what we should do to get you guys going, and we'll get right on it. And so with that, at 3:30 here Central Time, so we're pushing 4:30. It's getting late on a Friday. I'll turn it over to back over to you guys so you guys have the rest of the afternoon. But please be in contact with us as to what we can do to sort of help you get going. Stop.